All right, welcome back everyone. This is a quick review of the things we covered in class today and the things that we did not cover in class today. The key goals of today's materials are to introduce the OSI model as a framework for discussing all of the things that we'll cover in greater detail in future weeks, and also just to get you familiarized with some of the devices that are involved in networking that we did not have a chance to talk about. So we started off talking about how if we moved physical goods from point A to point B, there are certain things that could go wrong. And hopefully you captured the thought that similar types of things can happen in terms of moving something from point A to point B if it's digital, meaning that it could go missing or it could become corrupted. And therefore the theme of our class is like Scotty, except instead of beaming molecules around, we're beaming around digital bits, and we don't want them to get corrupted if things go wrong. Like in this movie, we got some weird new form of human being. We don't also want missing or malformed digital packets arriving as we move things around. As we talk about the overall way of thinking of communicating from one place to another, we have to keep in mind the ideas of a source, of a destination, of a medium like copper or light or sound, and some protocol that is used to communicate from point A to point B. So think of Pig Latin as a made-up language. Between any point A and point B, there can be applications running that have their own made-up Pig Latin-like languages. And so we'll learn about the types of protocols that we have in this class, but these are just the languages or the rules of communication between two devices, assuming that they can listen across some medium. Of course, we want to keep in mind distortion. We talked a little bit about the reason why the internet is distributed, because just like the military needs multiple paths to get from one place to another in case of disruptions, when they designed data communication, they thought, hey, sometimes paths could get broken, and so we need redundant paths to get someplace, and we need to ensure that it makes it there as well in case something gets lost. We talked about how there are two kinds of networks that we're going to focus on. One is the cloud in the middle here, and we would call this the regular internet, and this is an IP-based scheme, meaning that we pass around a certain we pass around packets of information that are addressed using IP addresses. And on our local area networks, we pass things around using Ethernet frames, which is another name for a packet in a local area, and we address things using unique identifiers, not IP addresses, but unique identifiers that are built in to each networking device, whether that's a wireless card or whether it's a physical network card with a cable plugged into it. They all have something unique. I played a brief video of Stanley, who is a janitor in a certain movie where he's just talking, and at one point after telling his orange joke, he starts singing the Bonanza song, dong 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 dong. And then I turned on Wireshark to demonstrate that there's a lot of traffic always going over Wireshark. And that's because computers are constantly broadcasting information. They want to find out questions like who's in the room, what other computers are around me. These are the things that they're trying to accomplish when they're doing that. And so because of that, we have to segment networks, otherwise we'll saturate all the bandwidth that's available. There are lots of different technologies out there that are part of data communications. And on the left-hand side here's actually the OSI stack, the different categories they could be put into. Some of the stuff on your right, you can actually see that some technologies are going to span multiple layers. Speaking of the OSI model, here it is more formally. What I'd like you to do is watch this 20-minute video from the slide deck. This guy does a fantastic job of walking through it. I couldn't do it any better. But here are some high-level ideas of what happens in each. In our class, we're primarily focused in the first 4 layers and then a little bit at layer 7. So we'll get to know, we'll revisit this pretty much every day in class so we know where we're at. So this will become clear as time goes on. But you will need to be able to explain this conversationally, what happens there. And so watch this video in order to do that. After you are conversant with it, I would like you to be able to, just in your own head, make up some exam questions if you were to pose questions about the OSI model, and that would probably result in the type of questions you would see on the exam if you're trying to make up your own. So it would be questions like what happens on layer 1 or what happens on layer 2, does this technology match this layer, that sort of thing. Okay, and I also wanted to bring to your attention that before the OSI model was created, there was another model, and this model was actually created in conjunction with the original ARPANET. So the original TCP/IP stack, some of the technologies that underlie the internet, they were categorized here into these four categories. So you have four categories as part of what is called the TCP/IP model, the Internet Protocol model, or the Department of Defense model because of where it came from. And so you want to be concerned about some of the naming conventions that are used there as we talk about things. So similarly, you should, after understanding what goes in what category, you should make up questions that would be related to the Department of Defense model, and again, categorizing like in which layer does IP addressing happen, or in which layer do we have a physical connection with a cable. So you should be able to make up those type of questions, and then therefore that would be the type of question you would see on an exam. In the class itself, these are the topics that we're covering approximately in any given week, and you can see that the topics primarily fit into certain layers of the OSI model. Another thing I forgot to repeat just now was that in addition to helping us categorize the many technologies that are out there, this stack also allows us from a conceptual standpoint to isolate portions of data communications and then to innovate and optimize in those areas, with the assumption that getting a better and faster cable doesn't mean that we need to necessarily rewrite how a web browser works. So you should be able to innovate in given areas and still have it communicate easily with the other layers. Okay, so let's talk about some of the devices that are involved in network communication. Just as some history, computers used to be isolated and not connected to one another. And so if you had, for example, a disk that was in a computer and you needed to take it somewhere else, you would walk, and therefore we would call it sneakernet, assuming you were wearing tennis shoes or sneakers. In the LAN area, the local area networks, there was some innovation that happened primarily out of the Palo Alto Research Center that was funded by Xerox. They created this technology where, using something that looks like your standard coaxial cable, that you could connect a whole bunch of computers into the one wire that is sitting in the middle of that coax cable, and then you would tap into it with this vampire taps and run a little connecting cable over to your computer, and then everybody could be listening to the communication that was happening there. So the good thing is that computers could then talk to one another. The bad thing is every single thing that, let's just say that this computer on the left is computer A and this computer over here is computer C. Anything that gets put onto the wire gets broadcast to every other computer. So if there's 3 computers and one broadcasts, everybody sees it. If there's 1,000 computers on the same network cable and one broadcasts, everybody sees it. And the problem is one of the problems is it saturates your bandwidth in terms of what's available, and you can't do other things if you're other computers. So that's kind of a bad thing. Our next kind of evolution in the devices we used were, we created hubs. And these are familiar looking cables, and this is an actual hub device right here on the left. Now, it looks like it would maybe be smart in that if I started a computer at the top here and then communicated to the hub, and let's say this is A and this is B, if I wanted to send something to there, it looks like maybe this device would be smart enough to not send it to everybody. But under the original functioning of the Ethernet, and if it's called a hub, then by definition this device is also a multi-port repeater, meaning all it does is electronically duplicate whatever comes in on one port, these holes. It just sends it out to everybody else. So even though the shape is different compared to tapping into one line, the technology was the same. It was still Ethernet if you're using a hub. So using a hub is outdated technology currently, as is this next one, which is a bridge. A bridge is kind of the same thing. Imagine if you had 2 networks. It's a little bit better. Let's just say I have PC1 and PC2 over here in the bottom left. If I say, hey, I want to send a message to PC2, I send it into this hub right here, and it sends it to everybody that's connected to that hub. But once it gets to that bridge, if the message looks like it's directed for PC2, the bridge actually knows that this PC2 is not located over here, and it'll isolate some of that traffic. But there's another type of traffic called broadcast traffic, and computers are doing that all the time. They're saying, like, who is next to me, in essence, or who has a particular IP address associated with them. even though ironically they communicate in MAC addresses. But they're talking all the time, and so broadcast messages do go over the bridge. So there's still a massive amount of communication happening if you connect LANs this way. Too much. So a bridge and a hub, because they don't filter enough traffic that's not meant for everybody else, then they're both kind of outdated technologies. So this switch looks identical to a hub right there, but it is a little different. And even though it's networked the same as you see on the right, the difference is if this is A and this is B and you have a message that goes from A to B, then this message only is going to go from A to B. It's not going to hit everybody else. So all modern local area networks work this way. This in the middle would be more of a corporate one. So back in your closets, your computers are probably connected to this through a jack that's in the wall if you're using wired connections. Or conceptually, you're doing something similar through your wireless networks and their access points and stuff like that. They're just going to try to get a channel directly between any two computers. So think about this. Like, what if you were sharing movies or other large files that were, maybe 100 gigs or something crazy big? That way you could have one, computers C and D are sharing a file, and A and B can be sharing a similar size file. And in contrast, if this were a hub, or if these things were connected via a bridge, then as one person sent 100 gigs to another one, it would just, until that was done sending, everybody's getting 100 gigs worth of data sent to every device. So hopefully that makes it clear why that's a bad thing. Okay, I talked about how there's local area networks, and then there's more of the traditional internet networks that are oftentimes across larger distances, and they're identified by IP addresses rather than local devices. Again, the issue is we don't want too much traffic being there, and we don't want any particular network to have too many devices connected to it. So we can actually connect different networks that are IP based via a router. So a router just separates traffic. And so some of these messages that happen in any given network, such as who is this or who is that, those questions get stopped at the router and stay confined to a given local area network. So on the right-hand side here, we have a depiction of some computers that are maybe in very different places in the world, and these routers allow us to connect. So if we send a packet or a message from one computer to another, such as 1 to 3, it goes through router 1, and then maybe router 2 and router 3, and then eventually it gets there. But a router, by definition, filters out a lot of the noise and the traffic that is on either side of it. It constrains and only communicates traffic that needs to travel across it. Here is and this is IP-based traffic, so there's going to be IP addresses associated with it. And this is what one of those looks like. Oftentimes they don't have a ton of ports on the back. They might just be connecting 2 or 3 things, but 2 or 3 different networks, but they transfer that data super fast. So again, over here on your local area networks, you're dealing with switches, which are concerned with MAC addresses burnt onto the networking devices. And in the middle here in the internet cloud, these are routers, and these are concerned with IP addresses. That's how they determine how to pass something from one place to another. Other things that are useful to know about is sometimes we use the word gateway, and I have a little star here because I want you to be careful with this. By definition, what a gateway means on a network is that it's similar to a router in that it connects 2 distinct networks, but the difference is with a router, they're actually speaking the same protocol. So it's similar but different. A router, for example, will connect 2 different networks that run the same protocol or method of communication, rules of communication, which in our case is IP. But what if you had a case where you wanted to go from an IP network and maybe connect to a cell phone, for example? A cell phone network is not technically an IP network. And so by definition, a gateway is actually connecting 2 different networks that use 2 different protocols, whereas a router is connecting different networks that use the same protocol. That's the distinction. Another thing that we talk about and we'll learn more about in the class is a firewall. So the idea of a firewall, and it looks like this on the right, you see this picture on the left where there's a stream of green data, 1s and 0s, passing back and forth between a network. Maybe this is a switch in here. Or maybe it's a router. The idea of a firewall is it's looking to filter out packets that don't belong. So Sometimes you purposely open up a connection, and sometimes you close down other methods of connecting with the network. Sometimes there's an outgoing request from a certain computer in here, and it's looking so, and when something's coming in, a firewall can say something like, hey, wait a minute, nobody made a request for that data, so I'm not going to connect you to them. So just generically speaking, I think the diagram does a good job of saying it filters out data. It lets in some data and filters out other data. And as we study this in the future, we'll be more specific about what type of data we can filter and not filter. Lastly, this is a device that we use a lot in our lab, and it is called an adaptive security appliance. And even though we talk about a lot of these other appliances separately, like a switch or a router or a firewall, this particular device is a convergence of many different things. Just like your cell phone does a lot of different things. It has a camera, it does phone, it does internet. This particular device does a lot of different things so that we can get some practice with working with switches, working with a router, working with a firewall. And so over time, we'll be doing different pieces of functionality that are built into this. So if you have a small business, this is a fantastic device to be able to do a lot of functionality you need. Technically, you could use this in a bigger environment, a bigger business. The difference is just, even though the device might look the same, it can get a lot more expensive. And even though it's running the same operating system on it with the same configuration tools, some of the higher end hardware that looks very similar is going to be able to handle just a tremendous amount of higher traffic that's crossing it. So, all right, here's a summary of terms related to things that I just went over. I hope that is beneficial for you in your initial study and in your review.